Hi, I recently purchased this Peak ESR 70 ESR and capacitance meter from Peak Electronic Design in the UK, mainly to help with troubleshooting faulty electronic equipment and also just when you're choosing capacitors that you may have had in storage for a while, just to see whether they're still kind of within spec or whether they've aged too badly. The Peak ESR retails for around £94 on the Peak Electronics website, and they also have an ESR 60 model which is slightly cheaper at £82. And they both have the features of being able to read capacitance from 1 microfarad to 22,000 microfarads. They both automatically start analysing your component as soon as you attach it to the crocodile clips, and they both automatically discharge any capacitors that are charged prior to it doing its tests. The difference between the two models is the ESR 60 can only read ESR from 0 to 20 ohms, whereas the ESR 70 can read from 0 to 40 ohms, and the ESR 70 also has a built-in speaker to make audible alerts when you're doing the testing. The device is relatively small. You can use it kind of handheld or just sit it on the desk, and it's small enough that you can easily put this into your toolkit if you're doing any work in the field. One thing I do think it's missing is some form of tilting bail, because it does kind of sit flat on the desk, and depending on which way you've got light pointing at it, you can get quite heavy shadows on the display, although the display itself is quite readable from most working angles. It does have a 2x16 LCD on the front, and then it's just got two buttons for the user interface, and then there's a nice flexible cable, probably about 30 centimeters long, with some nice gold crocodile clips on the end, and there's also a 2mm banana connector here if you wanted to use some probes instead of the crocodile clips for testing capacitors that are already in circuit. So what is ESR? ESR is the sum of all the ohmic losses of the capacitor, including the leads, the dielectric, and all the other materials used in the construction of the capacitor. It's a dynamic quantity, so it's something that's not measurable at DC. So normally you'd apply an AC frequency of 100 kHz to the capacitor and measure the ESR at that frequency. An ideal capacitor has no ohmic losses, but in reality there's always some series resistance, and this resistance is generally affected by the type, quality, and the age of the capacitor, depending on the chemistry that's being used in the construction of the capacitor. So what are the typical sources of loss within the capacitor? Well, first of all, there's the actual series resistance, which is caused by the physical resistance of the conductors used within the capacitor construction, so the leads and the capacitor plates or foils that are used inside it. And this just causes I²R losses, where I is the current flowing in the capacitor. Then you also have the leakage resistance, which is the DC resistance of the capacitor due to leakage currents within the capacitor, and this is typically a very high value and wouldn't normally affect the ESR reading. And then thirdly, you also have the dielectric loss. So due to molecular and interfacial polarization of the capacitor, you get losses that change with frequency applied to the capacitor. What is the result of all of these losses? Well, the energy is dissipated in the capacitor as the capacitor is charged and discharged. So just like you would lose energy as heat in a resistor, the capacitor can also heat up, which can lead to changes in the capacitor value, and in the case of electrolytic capacitors will actually end up causing further damage to the capacitor as the electrolyte dries up further. So why do we care about the ESR of a capacitor? Well, it's typically used to gauge the health of the capacitor under test, and at a certain point the ESR will start to affect the behaviour of the circuit. So for example, in an audio amplifier, the power supply might be unable to smooth the rectified DC once the electrolytic capacitors in the power supply have started to increase in ESR, which you would typically hear as mains hum on the speakers that are attached to it, or just in general the device may begin to malfunction and just not work at all. And if you have a faulty piece of equipment, particularly if you've noticed that it started to get worse in behaviour over time, the first point of call when you're opening up the equipment and having a look to see what's wrong is typically to inspect the capacitors and see if the ESR is normal and if the capacitors have started to bulge or leak electrolyte. Over time, and particularly accelerated by high peak ripple currents and high temperature, the electrolyte in electrolytic capacitors starts to dry out, and this is typically what results in increased ESR and eventual circuit failure in pieces of equipment. So how is ESR measured? As I said earlier, ESR is a dynamic quantity, so it can't just be measured by placing a DC ohm meter across the capacitor, as a healthy capacitor will block DC. What we need to do is apply a high frequency to the capacitor, and a typical standard is 100 kHz, and then given Ohm's law, where V equals IR, and we want to know R, we can either fix the voltage and measure current, so we use a voltage source and measure the current through the capacitor, or we can fix the current using a constant current source and measure the voltage across the capacitor. One of the ideal properties of an ESR meter is the ability to measure the ESR of a capacitor in circuit, so it's usually more likely that you apply a constant voltage so that you can set the test voltage low enough not to activate any semiconductor junctions in the circuit, and when you're applying your voltage to the circuit, you know you're just measuring the ESR of the capacitor. So some of you may be wondering whether the ESR for a given capacitor is an acceptable value or not. The instruction manual for the ESR meter has a table which gives a very basic indication for general purpose capacitors, and you'll see that actually the ESR value depends on both the voltage and the capacitance rating of the capacitor. So if we look here at the 100 microfarad capacitor, if it's only 10 volt rated, you can expect the ESR to be around 2 ohms or better, whereas if it's a 250 volt rated capacitor, it should be closer to 0.63 ohms. But the actual best way to know whether the ESR is acceptable is by having a look at the datasheet for the specific capacitor that you're using, and they should all say what the ESR or the typical ESR value is at the 100 kHz, which this device measures the ESR at. So here we have some technical specifications of the ESR meter. First of all, we can see what the peak test current and voltages of the device are. So you can expect plus or minus 20 milliamps to be injected into the capacitor under test, and the peak test voltage at full scale ESR is going to be plus or minus 40 millivolts. But if the probes are left disconnected, you'll expect to see plus or minus 2.5 volts on those probes. But at 40 millivolts, that's well below anything that would excite any semiconductor junctions on the board. So you can see that the ESR meter is ideal for testing your capacitors while they're in circuit. Then we have some accuracy specifications. So the capacitance we can see is going to be plus or minus 4%, plus or minus 0.2 microfarads. So it would give a good indication of the capacitance value of a capacitor. But if you've got something like a Fluke 289 or a Fluke 87, the capacitance readings on those are much more accurate. The ESR accuracy depends on the ESR, so the range that it's in. So if it's reading less than 2 ohms, you can expect the accuracy to be plus or minus 1.5%, plus or minus 0.02 ohms. And if it's greater than 2 ohms, you've got the uncertainty there of plus or minus 0.2 ohms on top of the basic 1.5% accuracy. The device has an automatic capacitor discharge circuit, so if the capacitor is charged to less than 50 volts, it will discharge that capacitor, otherwise it will warn you to carefully discharge the capacitor if it's greater than 50 volts. And it takes a standard 12 volt alkaline battery, and it will work all the way down to 8.5 volts. The device also has an automatic power off function, so after 30 seconds it will turn itself off. So now let's take a look at the operation of the device. So you can see we've only got 2 buttons on the front here. We've got a power button and a test button, and then an off button. So if you want to do repeated tests on a device, you can press the button here to trigger a new test. But as long as the device is powered up, as soon as it detects a new device connected to the crocodile clips, it starts doing a measurement. So if we now turn it on, you can see it gives us the firmware version, and then it says monitoring for component. So let's start off with a capacitor that we've got here, a Suntan branded capacitor, 470 microfarads, 25 volts. And if we attach the leads, It gives us our ESR value of 0.02 ohms and the capacitance is 500 microfarads. So if we have a quick look in our table, we can see at 470 microfarads and it's rated for 25 volts. So our ESR should be less than 0.29 ohms and it's well below that. Now if we have a look at a much larger capacitor, so this is a 4700 microfarad SAMWA capacitor, we attach the crocodile clips and you'll see it starts doing the test already. ESR of 0.04 ohms, but it's taken quite a lot longer to do the capacitance reading, although it has given it now, and it's relatively close to what it says. This is quite an old capacitor, it's been sat in my drawer for ages, so it's probably started to age a little bit. And then we'll just have a look at these three capacitors. So these are all 220 microfarads, starting with a nice high quality Panasonic FM capacitor. If we attach the probes, we can see the capacitance there, 218 microfarads, which is close to the 220, and then a nice low ESR of 0.02 ohms. Then if we try this Jamicon branded, still 220 microfarads. And you can see it has a slightly higher ESR of 0.12 ohms, but the capacitance is bang on at 221 microfarads. And then we've got a Hitano 220 microfarads. I don't know where this is from. I think it was something that I bought on eBay a long time ago. And again, we've got a reasonable ESR value of 0.12 ohms, and its capacitance value is actually slightly over what it is supposed to be, although within the 5 or 10% that we'd expect. So now if we have a look at these two capacitors, so these were taken off a faulty motherboard, and I don't know if you can see on this one, the capacitor itself has started to bulge quite badly at the top. And this was actually one of the faulty parts on the motherboard, and once I replaced this it worked, but I was able to just visually see that this one was starting to bulge, as I didn't have an ESR meter at the time. So if we attach the probes to this one, we can see we have a much higher ESR of 1.6 ohms, and it's unable to give us a capacitance reading. It just says in circuit or leaky, and that is actually the fault of this capacitor. So the leakage was so bad in it that it was unable to give any capacitor action to the switch mode power supply that it was in. This is also another one out of the same motherboard. It's rated for 1500 microfarads, but it gives a slightly interesting reading. So it's doing the testing now. The ESR is quite low on this, but the capacitance is way off. It's 3000 microfarads when it should only be 1500 microfarads. So I don't know if that's a quirk of the ESR meter not being able to read this one correctly, or whether it is actually slightly faulty. So we can do a test in a moment with the Fluke 87 and just see what it reads this capacitor to be. But you can see overall it's a nice simple device to use. You can just turn it on, attach your capacitor to the probes, and it will happily read the capacitance and ESR value of the capacitor that you've got. And then just to show it can be used in circuit, I have an old PCB here out of a DVD player that was faulty. I started repairing it, but in the end we ended up just buying a new one. So if we have a look at this capacitor here, which is a 68 microfarad 400 volt capacitor on the primary side, if we just put the probes across the, in fact it just turned off. If we just put the probes across the capacitor here while it's in circuit, we get our capacitance 60 microfarads and an ESR of 0.52 ohms. So it's way below what it needs to be. So it wasn't that part that was faulty anyway. But yeah, so it can happily read in circuit, and there is actually a transformer and some semiconductors around the primary here. So no problem reading in circuit. So here we have the Fluke 87 set to its capacitance range, and if we attach that capacitor that was reading twice its rated capacitance, we'll see what it reads. And it too reads twice the capacitance, so it's reading 3000 microfarads there as opposed to the 1500 microfarads. So that's quite an odd failure mode for a capacitor there. And if we also attach the one that was bulging, we can see what the Fluke 87 does. So that gives us a reading of 1300 microfarads. It's rated for 1000 microfarads, but the ESR meter wasn't happy with reading that one, and it was indeed faulty. So that just kind of shows that you can't just rely on a capacitance meter to tell whether a capacitor is faulty or not, because you would have thought, you know, if anything, that this capacitor was exceeding its specifications, when in fact it was completely useless in its application. So now let's take a look inside the ESR meter. So at the back we've just got three PosiDrive 1 screws, and these are just self-tapping screws, and the back just pops off. Okay, let's have a closer look. So here we have the insides of the ESR meter. At the bottom left here we've got the wires coming in from the component under test. And then we've got the GP23 12 volt battery, which is basically just 8 coin cells stacked together and then enclosed in an external housing. And this is a user replaceable part, so you are expected to take the back cover off if you need to change the battery. And then if we look here, we've got a relay here, which looks to be a double pole, double throw relay with a couple of resistors around it. So we've got a 33 ohm, probably a 1 watt resistor here, and then a pair of 150k resistors here. And this is probably the resistor used to discharge the capacitor if there's any residual charge. And then we've got a dual MOSFET here. So this is a Fairchild FQS4903 dual N-channel MOSFET with a couple of passives next to it. And then we've got four 74HC4066 quad bilateral analog switches. So these could be possibly switching in and out the constant current source for measuring the capacitance, or switching in and out the 100 kilohertz waveform. It's not quite sure, because that is quite a few switches there, but it depends how it does its measurements as to probably what they're using them for. And then here we've got two LMV324 rail-to-rail quad op amps. So these are probably generating the 100 kilohertz waveform for checking the ESR value, and it will also be amplifying the voltage that's read back before feeding it into the ADC on the microcontroller. And then just on the left here, we've got a small 5-pin SOT23 package, which is a Micrel MIC5205 5-volt regulator. So that's just a linear regulator for dropping the 12 volts down to the 5 volts for the microcontroller. And then we've got a few more passives and a few transistors here. And then we've got 4 transistors here, which look suspiciously like a H-bridge driver, which is probably for the piezo buzzer, which is on the other side for creating the audio waveforms. So if we have a look on the other side, if I can get it out of its case, you can see here we've just got the LCD itself, the piezo buzzer, a couple of tactile switches, and then you can see the battery that is actually kind of mounted through the board. But it seems to be a nicely made unit. We've got the in-circuit serial programming connector here for the microcontroller. So it's got an edge connector here, presumably for programming at the factory, but you could also solder on a header if there's a firmware update and program it that way. But yeah, it seems to be nicely made. The edge of the board is nicely milled out. Silk screen's good, and the quality of the soldering is really nice. So no complaints there about the assembly. So yeah, it's a relatively straightforward piece of equipment, so let's hook it up to the oscilloscope and do a couple of measurements to see how it does its ESR measurement and capacitance measurement. So I just realised I forgot to mention which microcontroller is used on the device. So this is a PIC16F886 8-bit microcontroller. It's a 28-pin device in an SOIC package and a fairly run-of-the-mill processor as far as these parts go. So it's just got a 10-bit A to D on there and an analog comparator, which probably is quite useful for the measurements that it's going to be doing. It also has a PWM generator, which it probably may well use to create the waveforms for driving the piezo buzzer using the H bridge that's just here. It's unlikely that it's doing the 100 kHz frequency generation using the PWM module, but it could well be creating 100 kHz just using an interrupt routine clocked off the internal oscillator. Okay, so what we have here is the ESR meter connected across a 10,000 microfarad capacitor, and then we've got the Rigol connected also across the capacitor. And what I'm hoping to do is measure, capture the waveform of what the ESR meter is actually doing to do the calculation of the ESR and capacitance. So if I start the single trigger and the test at the same time, so we can see here, this portion here is where it was doing the ESR measurement, and then we've got a series of triangle waveforms getting greater in amplitude where it's doing the capacitance measurement. So if you recall from school or from university, you can work out C by C times dV by dt equals I. So if we have a constant current I, and C is obviously fixed, we can work out our capacitance from the rate of change of voltage. So by looking at the gradient of this slope effectively, and if we find out what the constant current is that the ESR meter is supplying, we can work out the capacitance value. So I'll note down the values here, maybe we'll just check at the end if we can come up with the same value here, and then we'll switch out this for another capacitor. So I've just set up the cursors here to find the slope of this line here, and the difference in voltage here was 304 millivolts, and the difference in time from the start to the end of the slope was 1.58 seconds. So now we'll repeat that for a 1000 microfarad capacitor instead of the 10,000 that's in circuit now. So here we have the 1000 microfarad capacitor, and if we repeat the same test, so the time axis hasn't changed on here, and you can see the slope is much faster here, as you'd expect for a much smaller capacitor. So I'll redo the test with a slightly different time base. Okay, so here we've captured with a slightly faster waveform, and you can really see the ESR measurement here a bit closer. So again, here we've set up the cursors, and in this case this slope here changed in voltage by 820 millivolts, and that took 408 milliseconds. So now we'll repeat again for a 100 microfarad capacitor. So now we have a 100 microfarad capacitor connected, and we'll run the same test again. So here we have the waveform for the 100 microfarad capacitor, and now we can really see the ESR measurement going on here, which seems to be a series of pulses here, and then we've got this ramp again. So if we set up the cursors again, we can work out what the slope is here. So we can see in this case with the 100 microfarad capacitor, the change here was 916 millivolts, and that took just 52 milliseconds. So now we'll do one more test with a 10 microfarad electrolytic capacitor. So here we have the results of that test, and I'll set up the cursors one more time. And on this test, the slope here, the difference in time was just 6 milliseconds with a change in voltage of 1.112 volts. So now instead of using a capacitor, I'll just put this 1 ohm 1% resistor in place, and then as we know the resistance of this, we can work out what the constant current is that's going through the capacitor that's normally under test. So let's do that test now. So what we have now is, instead of a capacitor, I've put in a 1 ohm resistor, and if it does do the waveform to test out the capacitance, then we'll be able to work out what current is flowing through the capacitor under normal circumstances. It may well decide that it's not a capacitor connected, so we'll just see the ESR measurement and then it quits at that point. But anyway, we'll give that a go and see what happens. Looks like I missed it there. So actually it's just saying in circuit or leaky, which makes sense, but it's measured the resistance here, 1 ohm, and all we can see here is the ESR measurement. So maybe we'll just have a quick look, or a closer look at what it's actually doing there. So here we have a close-up of the 100 kilohertz waveform while it's doing the ESR measurement. So you can see here this is a nice square wave at 100 kilohertz with an amplitude of 52 millivolts peak to peak. So the device will be applying this constant voltage to the capacitor and working out the resistance based on the current that it's measured back. So now let's have a look to see if we can work out what the constant current is that it puts through the capacitor to work out the capacitance. So what we have now is the ESR meter connected through the resistor to a 10,000 microfarad capacitor. Then we've got the oscilloscope probe for channel 1 connected across the resistor, and the oscilloscope probe for channel 3 across the capacitor. So if I set this up for single shot and run the test, so now we can see the purple line, which is the voltage across the capacitor, which is climbing according to the constant current here, and then we have the voltage across the resistor, which we can use to calculate our test current. So I'll just write up the results from all of those tests, and then we'll just conclude the video. So here we have the results of all of those tests collated together. We started off with the 10,000 microfarad and went down to the 10 microfarad capacitor. We've got the measured capacitances here, and then we've got the delta T and the delta V of that final slope that we saw on the oscilloscope. And then obviously we've got our equation here. So if we put in a constant current I, we can work out the capacitance based on the delta V and the delta T. And then later on, as the final test, I put a 1 ohm resistor in series with the capacitor, and then put the two scope channels across the capacitor and across the resistor. And what we saw is, during those slopes, we were seeing approximately 2 millivolts being put through that, measured across that resistor. And then if we do Ohm's law, we see that that's approximately 2 milliamps. That value is going to be very slightly off because it was quite a noisy measurement on the oscilloscope. It doesn't really have the low-end small scale measurements for reading low voltages in the millivolt scale, so there's a bit of error there. And then finally, if we rearrange our capacitor equation to give us capacitance, we know, for example, on the 10 microfarad capacitor that we put in 2 milliamps, and then the delta V was 1.112 volts, and the delta T was 6 milliseconds. And if we do that calculation, it gives us 10.79 microfarads. The actual measured capacitance here was 10.41, so that's not far off. And then if we do the same for each of the other tests, we can see for the 100 mic cap, we were reading about 113 microfarads. For the 1000, we read 995 microfarads using that equation. And using the equation again, for the 10,000 microfarad capacitor, we calculate a value of around 10,394 microfarads. There is a bit of error there, obviously, because we are slightly uncertain about that 2 milliamp value, but you can see these are approximately correct. So that really shows that if you know what current you're putting through a capacitor, and you can measure the gradient of that slope, you can actually quite well work out the capacitance of the capacitor that's under test. So that was just a little aside to the actual review of the ESR meter itself. But overall, it seems to be a quite nice unit. It's got quite a few functions. The fluke meters that I've got are actually more precise for measuring capacitance, but in terms of ESR measurement, I don't have another piece of equipment that does that. And with this being around £90, and then I think delivery is £3 from the Peak website, it's a relatively low-cost piece of equipment that is really invaluable if you're doing any kind of electronic repairs. So I'd highly recommend that you buy this item if you are ever doing any repair work. It will save you a lot of time trying to work out whether there's a fault in the power supply section. So it definitely gets a thumbs up from me, and I'd highly recommend it. So if you enjoyed that video, please give me a thumbs up and subscribe, and thanks for watching.